as those aren't 0, then either lambda is 0 or x is equal to y. Question?
But lambda can't be 0 because if you can't distribute out a 0, can you?
Can't distribute out a 0.
Yeah, if you distribute out a lambda, like out of the x cubed and the y cubed.
As far as this algebra is concerned, lambda could be 0. Like looking at this equation, lambda could be 0, because if lambda is 0, this and this are 0, both sides are 0. Right?
But then the equation would still have to be true if the lambdas were canceled out, though. So then x and y would still have to be the same.
Oh, no. What do you mean? You mean if you cancel the lambdas? Remember, this is the whole point. When you have an algebraic expression, if you cancel these, you're promising me at that point that they can't be 0. Like, look at this equation. 4x equals x squared, right? If you cancel an x right now, then x equals 4 is true, but you're missing the fact that x could also be 0, and that would still be true.
Okay.
Right?
Yes, sir.
Okay. If x and y are both not 0, what we know is that lambda can be 0 or x can be equal to y, one of these. So now I have to look at both of those cases. Let's start with lambda being 0. Okay? Let's start with lambda being 0. So I'm continuing my thought here. I'm still working within this framework, right? I'm still under this assumption to begin. So all of this is just, let's see. So now we use this. Suppose lambda is 0. Okay, so I don't think I've used that before in here, right? That's the mathematical abbreviation for the word suppose. So now suppose that lambda is 0. Let's see if we can somehow squeeze out what x, y, well, we already know lambda would be 0, right? So let's see if we can squeeze out x and y. So take a look at the first equation. We're going to run into a pretty big problem right now. Equation 1. If lambda is 0, what does equation 1 become? Y e to the xy must be 0. And what does that force us to say? Y is 0, right? Because e to the xy can never be 0. E to anything can never be 0. So this would force y to be 0, right? Wouldn't it? And this gives us that. Have y'all seen that symbol before? Okay, well, you've seen the like double arrow like that, like this implies, that's what that means. It implies the next thing. Sometimes you can just use like a single arrow like this. They don't mean the same thing, but for here it's good enough, okay? So if you see this, what that is it's an arrow with an arrow going the other way. And they're hitting each other like this. And so this is what we call contradiction. Okay, so what we've made is a contradiction here. We've started out by saying, look, x and y can't be 0, blah, 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 then lambda must be 0, right? And then if lambda is 0, then y must be 0. But we just contradicted ourselves, right? So what does that mean? Lambda can't be 0. That's right. If x and y are 0, lambda can't be 0. We throw this out. Understand? As soon as we get a contradiction. We would have got a contradiction had we started here. Same thing, right? If lambda is 0, that's 0. That means x has to be 0. But we already started with the assumption that x and y were both not 0. So this is a contradiction. Thus, lambda cannot be 0. Which means the only way that this happens is if x is y, right? So now we need to look at that. So now suppose x is equal to y. If x is equal to y, then what can we say?
You can use equation 3.
Equation 3. Look at equation 3. Equation 3 tells us that if x is y, then basically I can replace either the y with the x, or I could replace the x with the y. It's my choice. So I'm going to replace that y with x. And this gives us 2x cubed is 16, which means x cubed is 8, which means x is 2. No plus or minus, right, because it's a cube root. And I believe that gives us the x and y coordinates that we need, right? So let's see if we can figure this out. We have that x is 2, right? And what's y then? 2, because x has to be y, right? And we never got the lambda from this. I'm not quite sure why I put another one of those. But we know that x must be 2, and then x has to be y, so y has to be 2. And could we get lambda from this? We could, right? We could just go to this equation right here, replace that with 2, 2, 2, 2, right? And couldn't we solve for lambda? And it would be some number. But does it matter in the big scheme of things? Like in the terms of finding the max and min, it doesn't, right? Having the lambda in this case doesn't help us solve anything. Do you all get that? So I'm just going to put, lambda is, well, shit, whatever lambda is. It's some number, right? Who cares about it? All right. It looks like we have an answer, don't we?
Yep.
But we're missing something.
We haven't checked the x is 0 or y.
Yeah, remember this assumption to begin? All right, remember this assumption to begin? So we need to consider this now. What if one of those is 0? What if just one of those is 0? Let's see what happens. So now this is a new train of thought. Okay, so like on my paper, I put a line separating everything I've done from what I'm about to do now. So now I'm going to say, suppose x is 0. I'll deal with y in a second. Remember, the first thing I started with is that they weren't both 0 at the same time, right? Now I'm just saying what happens if one of them is. What if x is 0 and y is not? And then I could do it the other way around, right? What if y is 0 and x isn't? So what if x is 0? What happens? If x is 0, is my first equation true? What does equation 1 tell me? If x is 0, equation 1, what would equation 1 mean?
I mean, y equals 0, and that doesn't make sense.
That would mean y equals lambda times 0, which means y would be 0, wouldn't it? Which is a contradiction, because I just said y isn't 0. Understand? So that would be a contradiction. And so that can't happen. So what should I consider now?
So if it contradicts one, then
That's it. Because remember, you have to satisfy all three at the same time. So what we're saying here is that we're starting out saying, look, suppose x is 0, y is not. Because we already looked at, well, yeah, let's just keep going. Okay, so right now, if x is 0, y is not, we know this can't be true, right? So that can't happen. Now, what if we do this? Suppose y is 0 and x is not. You get the same contradiction in which equation?
2.
Not in the first equation, right? In the first equation, we'd be okay. Because we'd have 0 here, we'd have 0 here, right? This would be 0. And this side, well, then you could say lambda could be 0, right? But in this equation, what would happen? If y is not, if y is 0, this is 0, no matter what. And then this right here, you would have x would have to be equal to 0. So that would be a contradiction, right? So equation 2 would tell us that x, I didn't put this last time, but it's e to the 0, which is a 1, equals 0. And that's why we say, x is 0. And therefore, this is another contradiction. Y'all following me? I think what gets challenging for students is like, when do I know I've covered everything? Like, when do I know that I've covered all the bases? Have we covered all the bases?
We have it covered if x equals 0, y equals 0.
Yeah, what if they're both 0? So what if both x and y are 0?
But isn't that covered by the x equals y?
That'll be covered. No, because that was totally different. Remember, our brain was in a completely different place when x was y. That's when they were both not 0,
Okay.
right? Yeah. So look, we're gonna write it down. Okay, we're gonna write it down because we need to actually logically explain this. Suppose that x equals 0 and y equals 0. Suppose they both equal 0. Then what about equation 1? Equation 1, 0 here, 0 there, they're equal, right? This one, 0, 0, we're equal. So equation 1 and equation 2 are good, aren't they? But equation 3 fails. Because if they're both 0, then that implies that 0 equals 16, which today at least is not true. We got 1 point, and that is it. What does that mean? And we're about to see.
It's like only like touching it, like maybe like the function's over here and our domain's over here, so it's like.
Yeah, we'll look at the picture. But let's just run through this all, make sure we understand this. The very beginning of the problem, we said, hey, look, let's suppose x and y are both not 0 at the same time, right? We ran through that, and we came up with x must be equal to y, and that x is 2 and y is 2, right? And then we said, okay, let's suppose one of them was 0 and the other one wasn't. Contradiction. Let's suppose the other one was 0 and the other one wasn't. Contradiction. Let's suppose they're both 0. Well, you got something that doesn't make sense, right? So we can satisfy 2 of them, but not all 3. So now it's a matter of determining whether or not this is a max or min, but you have nothing to compare it to. Do you? So this is very different. Let's go ahead and take our point. What was our point? 2, 2? 2, 2 lambda? Okay, so we have this point here. 2, 2 lambda was the only point of interest. And when we plug in 2, 2 into the function, we get e to the 4th power. I don't know if that's a max or min. So how can I determine if it's a max or min? I need to find another point that satisfies this that I can plug in here. So someone give me a point that I can plug in here, an x and a y, that would make that true.
Wait.
You already did that.
Yeah, 2, 2 won't work. Can't use 2, 2. Any other one. How about this? How about the cube root of 16, 0? Does that work? Is this point on that curve? Yes, right? Is that point getting plugged up into this function? Right? So it's on that curve. Whatever the heck that curve looks like up there, this point is in there, right? So if I plug that into that surface, what do I get? E to the, cube root of 16 times 0, which is e to the 0, which is 1. Right? So what can you tell me about this then? It's the max. Because it's bigger than that, right? It's bigger than this one? Now, I'm not saying that this is the minimum. I'm just saying that if I pick any other point, doesn't matter which one you pick, I could do f of 1 cube root of 15, okay? If I do that, will it work? 1 here, 1 cubed is 1. What's the cube root of 15 cubed? 15, and 1 plus 15 would be 16, and that would be there, right? But if you plug it in, what do you get? E to the cube root of 15, and that is definitely still smaller than e to the 4th. What's the cube root of 15? I don't know. Smaller than 4 though, isn't it?
Yeah.
But the whole idea is this. If Lagrange gives you one answer, then all you need to do is find any other point on your curve within your constraint to compare it to. If this number right here is bigger than that, you know it's the max. If this number is smaller than that, you know that's the min. All right? So we have an absolute maximum, we don't have an absolute minimum. Yes?
So in order for us to use those 2 points, we would have to satisfy all 3 of the equations. So in order for us, we use 2 and 2 because it satisfied equation 1, 2, and equation 3. And we plug them in.
Yes. Yes.
That way we can use x or y for that.
Yeah, so this 2, 2 is very important because not only does it live here, right? It also is a point that makes the gradient of this parallel to the gradient of that. And that's where we have maxes and mins, going back to that picture, right? So this is a super special point. It's on the curve, but it makes the gradients parallel. These 2 points I just picked out of my head, they're on the curve. I don't really know anything about their gradients though. What I do know is that the gradients, like at that point, the gradients aren't parallel. And at that point, the gradients of those two are not parallel. Make sense? All right, let's take a look at this. This is an interesting picture. I think, right? It should be pretty interesting to look at this one. I like it when I haven't taught Cal 3 in a while. I think it's been a couple of years since I've taught it. Because every time I go through these notes, it's like brand new for me. And so I'm like, what does this thing look like? Okay, so here's e to the xy. Whoa, look at this thing. All right. Trying to figure out where I can, yeah, all right, well. Okay, so you see this right here? This is x cubed plus y cubed equals 16. This is our domain on the ground. So if I take that domain on the ground over there, you see that's the domain on the ground? If I plug that into the surface, I get that thing. Do y'all see it? I'm going to pull this out. And you get that black curve. Do y'all see that black curve there? And we just found e to the fourth right there. That's e to the fourth. But if you look at it kind of from the side, it acts a lot like an exponential function, and it dies out and has like a horizontal asymptote. It like approaches zero, but it doesn't have a minimum. But also notice that our curve isn't closed. Look, if this thing came and like looped around itself, do y'all agree we would have to have a max and min? But see, this thing does not loop around to itself. That's the big difference in this problem, is that we don't have a closed curve. And that's a difference from what we did in the past. Questions? It's pretty powerful, isn't it? I mean, this technique, it's... okay, so I showed the work for that. Wow, it's already 2:17? What the hell? Shall we try this one? I think this will be our last one, if we can get through it. So I'm going to go right to it. First equation. Uh-oh. I'll let you think about the partials while I write down the conditions. I didn't tell you this at the beginning, but I've always found that the Lagrange section is one of the more challenging sections for my students. And I will also say it is my least favorite to grade, because it's just really hard to follow people's ideas, you know? So try to get kind of good at, write down words if you need to. Now I'm going to think that x is not 0. Try and explain it like logical steps rather than just a bunch of random stuff everywhere. What is the partial of f with respect to x? Negative 1 over x squared. Or you could say negative x to the negative 2, however you want to do that. So, and then lambda times equals lambda times. So I guess you could look at, yeah, this is like x to the negative 1 plus y to the negative 1. And then the other one is x to the negative 2 plus y to the negative 2 equals 1. So those are our two equations just rewritten so we can take derivatives a little easier. So derivative of that with respect to x is going to be negative x to the negative 2, which is that. And derivative of this with respect to x is negative 2 x to the negative 3. So I'll just put it over x cubed. The next one is identical almost, right? Except y's. And then our last one is our constraint. I'll just keep it written like this. Lagrange is a mathematician, by the way. And not to be confused, there's another one, another mathematician named Legendre, but they're different. So you might come across Legendre somewhere else. It's not the same person. All right, any ideas on how in the world we're going to get this thing going?
Assume, well, x and y can't be 0 because you can't divide by 0.
Yeah, so this is interesting because x and y can't be 0. Neither one of them. You can't have one be 0 or both be 0. And that's because the original functions are not defined at 0 for either one, right? So we don't have to consider that. We don't have to say, suppose x isn't 0, suppose y isn't 0, because we're assuming that to start the problem. Y'all understand how that's different than the last ones? Okay, so we know that this equation, we can work with this algebraically and not worry about multiplying both sides by x or anything because x can't be 0, right? So what could we do? I don't care. You just tell me what to do. I don't care.
Multiply by negative x cubed.
You want to go like negative x cubed on both sides there?
Yeah.
And we're not supposing anything on that, are we? This is just algebra. So if I multiply both sides by negative x cubed, what do you get? You get x equals 2 lambda. So I'm multiplying both sides by x, negative x cubed, and not worried about the fact that x can be 0 because it can't. This one right here, same thing, right? So this is going to be y equals 2 lambda again. Well then what?
Set them equal to each other.
Yeah, well that means that x has to be y, right? So if you want x to be equal to 2 lambda here and you want y to be equal to 2 lambda there, then x has to be y. So therefore, this is our 3 dots means therefore. You learned some symbols today, I guess. That means therefore. So therefore, from equation 1 and equation 2 tell us that, I'll just write it out, x equals 2 lambda and y equals 2 lambda, so x must be y. So if x is y, then I can go into the third equation. And I can replace all my y's with x's. And then get a common denominator there. And then multiply both sides by x squared, not worrying again that x can't be 0, so I don't have to worry about it. And then this gives me 2 solutions, plus or minus root 2 for x. So we picked up some points pretty quick here, didn't we? This was not that bad algebraically. So what we have is this. We have x could be root 2, x could be negative root 2, and then what must the y be? Exactly the same as the x. So this would be root 2, and then root 2. And then don't we have some lambdas here?
Second one, is that the y is negative?
Pardon? Oh, yeah, sorry. Thank you. This was negative because they have to be identical. There we go. Now, I didn't put lambda in here, but, you know, we could just solve for lambda, couldn't we? But we don't care about lambda too much. We only care about lambda if we need it to solve for something, to solve for the x or the y. All right, are we missing anything here? Is there anything else that could happen? Yeah, I mean, the only possibilities here, the only thing that would make this true is if, I mean, the most you could say is maybe like, you know, if lambda is 0, then, you know, x would be 0, but we already said x can't be 0, so lambda can't be 0, and, you know, there's just nothing else algebraically left. This one is almost so clean, it's hard to tell that we're done, but we are. Now we have to figure out what the max and min are, but I think it's pretty easy to tell which one's going to give you the max, right? Because these are positive numbers. So when you plug that in here, you can get a positive number, and when you plug these in here, you get a negative number. So I won't plug them in. I'll let you plug them in. Let's just take a look at it. Wow, okay, this is a crazy looking surface. This surface is really crazy because the surface is not defined. The surface is not defined anywhere along the x or y axes, because anywhere along the x-axis, y is 0, and along the y-axis, x is 0. So if you look along the axes here, right, like we're looking from the top along the x and y axes, our function isn't there. But as you approach the x and y axes, you have asymptotes. So like you've got these asymptotes going up and down. Now you can't tell from this picture, but at 0, 0, it is undefined. You can't tell from the surface. Now, that's our surface. This is our constraint. So if we look at our constraint plugged in, so here's our constraint on the ground. Here's our constraint plugged in. Let me take everything out. It's kind of cool to see it, but this is our constraint plugged in. And so what we found were that highest point and that lowest point. What is this? I don't know what this is. I think it's my viewpoint. And it's not working apparently. All right. Yeah, it's a good place to stop. I mean, we'll look at this, but we won't do any problems. Well, what time is it? 2:26. We want to talk a little bit about the exam or no? Okay, so Lagrange, the great thing about Lagrange is it extends. So if you have a function of 3 variables, subject to a constraint equal to a constant, your constraint function is now at 3 variables, then it's the same exact process. You just want to know when the gradient of f is equal to lambda times the gradient of g. And then you want to make sure that your constraint is maintained. The difference here is that because when you take the gradient, you get partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z, you now have 3 equations up here and 1 equation down here, which gives you a total of 4 equations and 4 unknowns. So you'll be solving for x, y, z, and lambda, which becomes somewhat problematic, right? You can imagine you've got more things to keep track of now. And then here's some examples we'll do. But then you can have a function of 3 variables subject to 2 constraints. And if you have that, then you have to throw in this new thing. And this we'll do this later, but the algebra gets crazier. You have 5 things you have to solve for. So you have 5 equations and 5 unknowns, and all nonlinear equations. Yeah. And then I made some calculators. Oh, but that doesn't really matter if you don't have this program. But if you had the program, I made these calculators where you can just plug in the different things and it'll calculate it all. All right, the test. So let me just go back to where we left off. We left off right here. So the test. The test is on Wednesday. That's it. Y'all have a good one. I don't know. I mean, what do you have questions over? Is there anything you have a question on?
Are we allowed to bring formula sheets or like?
I'm glad you asked that. Yes. Let me just take a look at this real quick. Where the heck is the test? I don't remember where I put the test now. Pardon? Yes. So you can bring all the formulas that are in Canvas to the test. And let's say you can have one additional sheet with any formulas, steps, or procedures you want. No worked out problems. All right, so if you need to write down the formula for finding the distance between a point and a plane, write down the formula, but don't like give yourself an example. Okay, if you don't remember the formula for anything, you can put it on that sheet of paper. So just a single sheet of paper, front and back, all right? There's nothing worked out on it. Yes?
Sir, so you mentioned that the homework would be good practice for the exam.
Uh-huh.
Are there any like specific problems from each section that you would recommend, or do you not know?
Well, let me try and narrow it down for you, all right? The test is 10 problems. Let me just I'm not going to tell you what the problems are, but I'm going to tell you the types of things you're going to need to be able to do. You have to be able to find the equation of a sphere, right? So you need to know like what the equation of a sphere looks like. You need to be able to take a look at like a quadratic surface. Remember all those quadratic surfaces? Like ellipsoid and all those, right? All those different shapes we had.
Like identify them?
Not identify them. What you're going to need to be able to do is do something with completing the square. Because when you complete the square, remember you're able to find the center. You're going to need to be able to find the center of some sort of quadratic surface. You do need to know the shortest distance between a point in a line and a point in a plane. Those are formulas, but more importantly, you need to know how to construct it. You know, you have to create a vector and finding the vector equation of a line. The vector equation of a line that is tangent to a curve. So I give you curve, you give me tangent line. That's in the vector form. If I give you an acceleration function, can you recover its position function? Showing a limit doesn't exist. So that was that one where we were trying to find limits, so we had to like look at different paths. And to show it doesn't exist, you have to just show it goes to two different things at one time. I mean, not one time, at two different things along two different paths. I'll be able to do the chain rule, where you do that like tree diagram. Directional derivatives. Know how to compute a directional derivative? What was one of the most important things with directional derivative, if you're going to use the formula for it? What was one of the most important things?
Making sure the direction.
Yeah, in the formula, you use a vector u, which is a unit vector. You have to make sure the vector is a unit vector. Yeah. Finding the equation of a tangent plane to a surface. Remember when we did equation of tangent plane to a surface, there were two formulas given. One was given early in the class, and that only worked if you had a function of two variables. So you had like z equals f of x. But then later on, I gave you a more general formula that worked whenever you have any surface of three variables. So be able to use either one of them. And then find the extreme values and saddle points. So basically find your local max and mins on the surface. That's computing capital D, right? And then finding the absolute max and min of a surface on some closed bounded region, which would be last class. Nothing from this class is going to be on the test. I think I pretty much just laid the test out there for you right there. The question will be, when you come in, how much time is it going to take you to figure out what to do? You know, so part of this test is efficiency, right? You look at it, you get right to it. If you're taking 10 minutes to just sort through what to do, then time is gonna be your enemy. Because we have 100 minutes and you have 10 problems. That's 10 minutes a problem, and some of these problems take longer than others. Like these last ones where you have to find, like, you know, the closed bounded region. Like we did problem class, took us 30 minutes, right? So some of these should go fast. I would hope some of them go fast. We'll see. It's 10 problems, so.
Would the mini exams be good study material as well?
I don't think the mini exams are good study material But the whole theory behind that is if you can do the mini exams, then these problems should be relatively easy compared to. Like level of problem is relatively easy. Yeah, like the integration that you have to do is not going to be any crazy integration. I mean, I don't even see any integration that's, I mean, of course, derivatives you'll have to do a little, you know, product rule or something, but, you know.
I was saying, like, technically, if we do the take-home, like, the mini take-home exams for practice, like, we should be pretty set for the midterm, like.
I think if you've done all the mini exams and you understand all the problems and how they were done, and then I think that you would then be at a level that is higher than what this test is going to ask of you. This test is going to ask of you very just straightforward questions. Find the directional derivative. Here's the acceleration function. Find the position function. But you need to recognize it when you see it. And I think the homework is where you'd recognize these problems from. The mini exams, these won't look like the mini exams problems. So study your homework. Yes, I think that's the most important thing, is to study your homework. I think I've narrowed it down a little bit. I don't know. Does that sound narrowed down, or does it sound like... Okay. All right, so remember, I won't be here Wednesday. I won't be here Wednesday. I'll be here tomorrow in my office, but I'm leaving out of town, so Wednesday we'll have a proctor, and he's just going to come in and give you the exam. He's going to spread you all out and then turn it in and leave. My plan is I'm going to be back in town on the Tuesday during spring break. So I'm going to come in to my office and pick up the exam. I'm giving 3 exams this week. I won't be here for any of them. So I'm going to pick up all the exams and then I'm going to grade them. So I'm thinking sometime in spring break I'll post grades on these. All right. Have a good one. Y'all all have a good spring break if I don't see you before. Be safe. Let me turn this camera off.